Hello everybody. In this video, I'm going to go through those last two halogenation addition reaction practice questions that are on the next page. I just wanted to briefly review. In class we learned about this other addition reaction where a halogen is added. We represent that as X2. That can be bromine, chlorine, or iodine, as we listed at the top of the page there. It's key that both atoms, the two bromines or the two chlorines or the two iodines, add to the two carbons that are part of the pi bond, and they add through anti-addition. So they always, in the product, will be anti to each other. So here's the mechanism. I won't go through all these steps. We'll do an example that is on the next page. So at the end of class, we predicted the products for this first reaction with the cyclohexene and chlorine. So let's do this mechanism. And then we'll do the next practice problem as well. So Cl2, that is the reagent added to the double bond. So I'm drawing that out here. And the first step involves the double bond, creating a bond to a chlorine, chlorine to chlorine bond breaks, and the same chlorine that receives electrons from the pi bond also creates another bond to that, and that's how we get that three-membered ring. So the intermediate formed here, now we have to include stereochemistry, or at least we're going to for this mechanism. That chlorine has two bonds to the ring, one to each of the carbons that were part of the double bond. Now that three-membered ring, so the two carbons in the chlorine, that smaller ring on the right side, can be drawn what we've done so far, which is, quote, below the ring, or it can be drawn above the ring, which I will draw here, where we're just using wedges instead of dashes. And then our other product or intermediate formed in that first step is Cl-. Okay, so second step, that Cl- forms a bond to one of the carbons in that three-membered ring. And then that carbon to chlorine bond at the same carbon breaks, and those electrons will go back to that other chlorine. So I drew the same arrows. I'll draw the product for the top reaction first. So the chlorine that was part of the ring, I'll make it orange here, chlorine part of the ring, that one remains on the dash bond, and its bond to carbon 2 did not break. So at carbon 2, it's still on a dash. I'll number these again. It's still on a dash bond. Now the Cl- that came in, I'll just leave that one drawn in blue. That one came in if the opposite to where that original orange chlorine was. So the orange chlorine in this intermediate is drawn on dash bonds. That blue chlorine must have bonded above the ring on a wedge. And this is how we get the anti-stereochemistry in this product. I told you stereochemistry in class, so I'll just rewrite those here. These are both R, and then you can double check that, make sure you can identify why there are. Product of the other stereochemical option, the orange chlorine remains on a wedge. And now the other chlorine is on a dash. And then these are S and S. So these two products are enantiomers because while there are two stereocenters, both change configuration R to S when we're comparing them. So these are enantiomers. Okay, so let's do this next one here. I'm just going to scooch this up to give us some more room. All right, so now we have an alkyne. So this is where it matters if we have one or two equivalents of the molecule that's getting added to the pi bond. So in the first option, we have one equivalent of Br2. So we'll have only two bromine atoms, Br2, that will be added to the carbon-to-carbon triple bond. And it must remain as a double bond because we can only add those two bromine atoms once. So we know we have a double bond between those two carbons. And then each one gets a bromine, and we still have to apply the anti-addition. So if the carbon on the left has a bromine bonded there, then the carbon on the right better have the bromine bonded opposite. So now it has a H, and then this one has a CH3. So in this case, the halogen being added has the highest atomic number, and so we will always form these E-alkenes because of anti-addition. The two high priority groups are on opposite sides of the double bond, and that is an E-alkene in this case. Next we have Br2 with two equivalents. So with two equivalents, another set of two bromine atoms is added to the double bond. Now we're forming tetrahedral carbons here, so we still have that central carbon-to-carbon bond. We have Br, the original Br. We have a hydrogen, and then I'll add another Br here. On the left, we have original Br, methyl, and another bromine. Now, with this product, when we ever form a tetrahedral starting from sp2 carbons, trigonal planar, to sp3 tetrahedral, we need to consider if a stereocenter is formed. But in this case, because we're adding the same two atoms, so two bromines to each carbon, neither of them is chiral. Neither carbon is chiral. So usually, if you start with an alkyne and add two equivalents of some reagent, you typically don't form chiral carbons because the same groups will be added to the same carbon, and then that prevents it from being chiral. We don't have four different groups bonded to each individual carbon. Okay, let's briefly go through hydrogenation addition reactions. So they have some similarities and differences with the halogenation that we just completed. Notice that H2 is the reagent that's added. And if we compare starting material to product, and if you want to pause the video and just try to identify what's different between the starting material and product, certainly do that. There are two new hydrogen atoms bonded to the alkene carbons. And in this case, they're bonded on the same side where we now have syn addition. Again, this is stereoselective, meaning it's selective. The H2 selectively adds syn to each other or on the same side of the double bond. We'll explain, we're not going to draw out the mechanism, I'll just go through this image here shortly. We'll explain why it is syn addition only. So halogenation adding Br2, Cl2, I2 is anti-addition always. Adding H2 is syn addition. Now to add hydrogen, it's really not easy to take an alkene molecule, these are liquids, sometimes solids, take that molecule and bubble hydrogen gas, so H2 exists as a gas, just bubble hydrogen gas with that solid or liquid, a reaction doesn't really occur. So a catalyst, something that helps the reaction proceed, is required for this reaction. So catalysts are palladium, so you see that here. Palladium, platinum, and nickel. One of the three can be used to add hydrogen to an alkene or an alkyne. Okay, so how do we react this metal catalyst with the gas and then with the double bond? Well, first you have, or a researcher, if you're the researcher, you have this metal catalyst surface here, and then that will react with hydrogen gas that's provided, so bubbled onto this catalyst surface. In the hydrogen gas, the H2 molecule will bond to the metal surface. So now we have individual hydrogen atoms bonded to that surface. And the alkene, I'll use, let's see, green here. The alkene will also bond to the surface, and notice that one of the pi bonds, now it's like 1 electron per carbon that's on that surface. There's no pi bond between them anymore. So then when you have both hydrogen atoms and what was the alkene attached to the catalyst surface, new bonds can be formed. Now these are drawn, like this first image where I have all these different colored highlights. The alkene and the hydrogen atoms are drawn far apart, but remember that these are so small, they can get very close to each other. And so being near the carbon electrons that are currently being shared with the metal surface can then create a new bond to a hydrogen atom, so that this new bond, I'll circle it in orange here, is created between the carbon and hydrogen. And then the other carbon can do the same thing. It creates, using its electrons, will create a bond to another hydrogen atom, and then we've got that other hydrogen bonded there, and we have the alkane now. And that's really all for the mechanism, but now that you can kind of visually see that the alkene bonds to the metal surface like this is why we have syn addition. The two carbons are like laying flat on that metal surface, so that the hydrogens being added are adding syn to each other, so on the same side. Now, I won't ask you to reproduce this mechanism like I will for others. I won't ask you to kind of draw a metal surface or anything like that. This is here to help describe what is observed, which is the syn addition for the H2 with the catalyst. So I'll end the video with this concept, and in class we'll do practice. We'll more be with these sets of reagents, the H2 and the catalyst, predicting products, or if we're given a product, predicting the starting material. Okay, we'll be done here. We'll continue notes in class.